Okay. So, the last class we were talking about linear regression. We started with linear regression, right, and we talked about various machine learning use cases etc., where in which case what methods become applicable, like association analysis, and we talked about supervised, unsupervised, semi supervised, and reinforcement learning kind of ideas, right. So, today we will get into supervised learning, especially the basic technique, which is building a linear model between two random variables. Okay, remember we talked about two random variables. We will try to build model between explain a random variable using another. Okay, and and this is a continuous variable. We will be predicting a continuous variable. We will soon learn to predict discrete outcomes, which will be logistic regression, but today we will talk about continuous variable, explaining the continuous variable using a model. And if you look back, that is what we have tried it in ANOVA, but we did not derive the values of how to get the sum squared error, mean squared error, and so on. So, today we will learn that as well. Okay. So, we will introduce formally linear regression, and there is going to be a lot of writing and assumptions. So, my model that I am going to build, I call it as M, is going to be, I want to predict a random variable y. So, the prediction I call it as y hat, which is what I am going to predict about y. So, that is y hat, and let us call this as beta 1 x1 plus beta naught. This is similar to your what I call your mx plus c. If I want to write it in vectorial fashion, y vector equals to, how do I do that? What will be your x? What is your capital X? In this case, what is your capital X? In this simple example, y equals to beta 1 x1 plus beta naught. What is your x? If I want to write it, x is in a compact form, like a matrix or a vector or whatever. What is theta first? Let us write theta. What is theta? Beta naught and, or beta 1 and beta naught. What about x? What about x? This will be x1. x1 is a vector or a matrix, is a single number. x1 is a vector or a number? Vector of what? Observations, right? Vector of observations of the the input, right? So, x1 is a vector. So, this is x1, and what is this? 1, right? If I want to append it, I will just append it as 1, because the weightage for beta naught is what? 1. So, let us say this is, what is this? This is 2 cross 1 size, and what is this size going to be? Let us say there are n observations, capital N observations. So, this is n cross 2. So, this will make sense, n cross 2 into 2 cross 1. So, that is a n cross 1, y hat is going to be n cross 1. This is in a compact matrix form, right, make sense. Okay. So, you understand why I have written numerical value 1 n times, because the weightage for beta naught is 1, and this gives me an idea to extend it easily to what? Let us say I have multiple variables, then this gives me an easy way to extend it, where x will be x1 up to xn times 111, right. So, this will become what? N cross, let us say there are m variables. So, this becomes an n cross m matrix, and what will be the parameter size? Parameters will be m cross 1. If I extend it in this case, the parameter will be beta 1 up to. So, I can easily extend this to a multivariate form as well, if I write it in this matrix form. Okay. So, y hat equals to capital X times theta. Okay. So, this capital X we call it as a regressor matrix, regressor matrix. Okay. So, this is what basically it is what explains the relation R. It contains all the inputs that will explain your output Y, right. So, that is what it is regressed. So, this is your regressor matrix and your theta is your unknowns, unknown parameters to be estimated during training. Clear? Understood? Okay. So far so good. This is about the model that we take. Okay. This is the linear regression model that we are talking about. Clear? So, this is Y hat. Okay. Make sense? Okay. Both single variate or multivariate regression, okay, univariate or multivariate regression. Now, if we are building a model, when can I say this model is good or bad? There are two questions here. When can I say first the model is good? The other one is when can I say that my estimates, suppose I estimate theta using some methodology, when can I say that my theta is good, right. So, to all of this, to answer all these questions, you need to know what is called as the ground truth, the reality. So, I am going to make some assumptions about the truth. Okay. So, truth I will call it as T, the ground truth which is never known, which I am assuming. When I write truth, I write it as Y, I do not write a hat because this is the truth. I assume that the truth is also generated using a linear model, okay, but with a noise. So, if I write it as yi, it is going to be epsilon I, okay. I will generally write it as epsilon because the earlier I have not used. So, or in other words, if I write it in a matrix, vector matrix notation, it is going to be where epsilon is a vector, which is a noise. Why am I assuming there is a noise? Remember, we are only modeling the random experiments, the outcome of random experiments, and the outcome of random experiments will never be a deterministic one. So, what you may get in reality, you may, let us say you have Y, you have X. So, X is your input. Let us say I have 5 inputs 2, 2, 2, 4. You may get output as what is your beta 1 in this case? What is your beta 1? I have 5 y values and 5 x values. Can you tell me what is the beta value? Is it 2? Is it exactly 2? 2 will not fit this every equation, but how many beta values I want? I want only one beta value. I assume that there is only one, there is a relation between y and x which is governed by this beta, but I do not have multiple beta values, I cannot fit multiple beta values, I can only fit one beta value. Now, y is the variation. If beta is 2, then I know that it is close by, but it is not exactly matching. Why is not it exactly matching? Because of the nature of the random experiment itself. So, that is where I am going to assume, look, y is almost closely explained by, the variability in y is mostly explained by x, but of course there is a variability which cannot be explained by x, which is attributed to noise. You understand? So, the variability in y we want to assume like exactly like ANOVA, right. The variability in y I want to explain using x, but I cannot fully explain it because there is always some certain sort of uncertainty, and that is the reason why I assume epsilon, which is my noise. Now, the question is, noise can also be modeled. It is not that the noise cannot be modeled. So, if you look at weather, we try to predict weather, forecast weather, we try to forecast patients, whatever the remaining life, etc., how what is the most likely duration over which the patient can survive, etc. We do lots of predictions, right, the half life of a drug, etc. But in this case the assumption about noise is what? I assume that the noise cannot be modeled. That is why when you fit y equals to mx, you do not fit a model for noise, you assume that the noise epsilon is unmodelable, and this is a usual assumption we make about the noise. So, epsilon is going to follow, what is it, normal distribution 0 comma sigma squared, and this is going to be IID. This is the usual assumption we made in even in ANOVA. So, this is the same assumption we are making, epsilon follows or noise is Gaussian distributed or normally distributed with mean 0, variance is sigma squared, and here they are IID, that they are all independent. Okay. So, let me write down the assumptions. So, first assumption, epsilon is, this is the assumptions I make before I fit the model, okay, only then the model fitting, and linearity assumption is already there. The moment I write the equation of truth, I assume that the model, the truth is following a linear model, linear relationship, okay. Otherwise I cannot compare the truth versus model, because if these two are two different model structures, I am at loss, okay. Then this is a big assumption we make, okay. If you see, the reason behind understanding these assumptions is, if you remove these assumptions one by one, you get different methods, that is the most interesting part. So, this is from Gauss time 1800s, but till date linear regression is valid, because if you start, once you understand linear regression with these assumptions, if you start removing the assumptions or relaxing the assumptions, you develop different methods, okay. So, your assumption on noise, if you remove, you will get a method, I will tell you that. So, you have linearity, you have excess deterministic, any other assumption you could think of? Okay. So, this is a important assumption we make, y is homoscedastic, meaning the variance of y is fixed to be what? Is fixed to be sigma square, which is the variance of noise, okay. We will see graphically what this assumption means, okay. I will show you graphically what this assumption means. So, these are the key assumptions we make, okay. X is deterministic, y is homoscedastic, linearity assumption, the assumption of noise being Gaussian, and IID, okay. So, let me go to this fourth assumption and then tell you what it means. So, this is what I mean when I say homoscedastic. So, if you plot x versus y, remember for every x there could be multiple values of y, that is what I showed you in the example, 2, 2, 2, 4, 4.1, 3.9, like that, right. So, now at every value of x you plot y, all of them follows roughly Gaussian distribution. Look at this, I have plotted here, it follows a normal, and the variance for each value of x is what? The variance in y for each value of x is sigma squared, the same. So, you understand what I mean. So, the variability here, close to that this region. So, if I talk about variability is kind of fixed and all of them follow a normal distribution. The variance is fixed to be sigma squared. If for whatever reason the variance is increasing, which will happen in your stock markets in many of the data in your even in your biomedical data, if the variance starts increasing, then linear least squares is not a good method. Okay. Only under these assumptions we will show that linear regression is a best method, but if any of the assumptions are violated, then linear least squares is a suboptimal method. So if this variance starts increasing like the other figure I have showed y versus x, then you cannot fit what is known as homoscedastic model like linear regression, you have to go to heteroscedastic models, okay, where the variance assumption is not kept to be constant. Okay, you might have done linear regression for ages, but these are the underpinning assumptions, okay, the assumption of homoscedasticity. Now you understand the assumption of noise as well, right? What is normal 0 comma sigma square, at every value of x the distribution of y is normal and it has the same variance, and your input. So if you assume that your input is your noise is not uniform, or sorry, if it is not IID, you know that you can fit a model for noise, and there are models that fit for noise, cater for noise. So you will see that there are filters like Kalman filters and other methods like ARMA processes, RMAX models, where there are models separately fit for noise as well. You assume that the noise itself is modelable, whatever explained by x not explained by x is still modelable, then you have a different method. In this case what are you saying? Whatever that is cannot be explained by x is not modelable. You have to be very clear with the assumptions. Whatever cannot be explained by x is not modelable, then you go for linear regression. If you think x is not the only thing, but there are something else can be explained, so you can fit a noise model, then you go for different methods. Okay. So noise model, we do not fit a noise model here, okay, but if I relax that assumption, then I can fit noise models and then you get different methods, okay. And so what else I had, sorry, I think this is what I had, and then we have linearity. The moment you take in non-linearity, then it could be you open up a big box, non-linear regression, all of those techniques. Here we assume only linear relationship, and x is deterministic. This is very important. I do not assume noise in x, that is input is completely controlled. If your input has noise and if it is significant, then you cannot use this method, then you have a method called error in variance, okay. This method is not applicable, okay. So for every assumption, if you relax, you develop a newer method. So in this case x is assumed to be completely known, deterministic, okay. The last assumption I told about y is homoscedastic. So this is the assumptions that I make about the truth, and with these assumptions I am going to fit a model, okay. Now as I told you, when you talk about, there are ways, many ways in which you can develop. So what is the unknown? The unknown is only now theta, the parameters beta 1 and beta naught, because what did I do? I have made assumptions that it is enough to fit a beta 1 and beta naught. There is no model for noise, x is deterministic, it is homoscedastic, noise is homoscedastic, y is homoscedastic, noise is Gaussian, 0 comma sigma squared. These are the assumptions about truth. Once I make this assumption about truth, then what do I need to know? I need to fit the model, obtain model parameters from training data. Remember, this is a supervised learning, so I am going to find out the parameters from training data. So what is going to be my objective? I am going to call this objective as j. What is it I want to do for j? What kind of objective function? I can do absolute error or squared error, mean squared error, which is the common. So I am going to have, let us say, mean squared error, So what do I want to do? Minimize this function j, which is what, summation 1 over n summation y minus y hat the whole square, and by varying what? By varying beta naught and beta 1 such that y hat is what? Clear? So this is my optimization formulation. So it typically is this: minimize j, and objective in this case, which is the loss function, we call this as loss function. Okay. So this function is called as loss function because you want to minimize this loss, right. You want to minimize the loss, which is, loss is nothing but error, right. The y minus y hat the whole square is error, squared error. So this is also the loss function called as L sometimes. Okay. In machine learning we call it as L loss function, which you want to minimize this loss function, which is the mean square error. Okay. Subjected to by varying parameters what? Beta naught and beta 1, such that what ST stands for, such that what is the y hat? Y hat should be equal to beta naught plus beta 1 x1. This is what I want to do. Clear? Simple? Okay. Now in general we know why, if we minimize, in general what do you want to find? When you want to find parameters, the solution to, okay, let me show it here. So when you want to predict y in general, when you want to minimize MSE, solution is going to be what? Expectation of y given x. We know that in general when you minimize the squared error, what is the solution? The solution is going to be mean, right. That is what we showed you, we derived in the earlier sessions, that when you want to minimize a squared error, it is nothing but the solution is going to be mean. So what are we trying to predict? We are trying to find out or figure out the average value of y. In this case x is given to you. So what is the solution? The solution is going to be expectation of y given x. In our case we have assumed this to be you could have expectation of y given x to be a non-linear form, you could have expectation of y given x to be some multivariate regression, non-linear regression, blah blah blah. In this case what am I assuming? The average value of y given x is following a linear form. That is the assumption, or that is the framework of linear regression. So now how am I going to find? So once you understand this, it becomes easier. How am I going to find now the parameters, unknown parameters? You have to minimize the objective function with respect to right, of course beta hat, and make it to, this is could be a minima or a maxima point, because both at the minima point, that is the bowl, and the peak, the slope is 0, and when it is a minima point, both the sides the slope is going to increase. So the second derivative is going to be positive, and if it is a maxima point, both the sides the derivative is going to be less than 0. So it is going to be rate of change of derivative is negative. So for a maxima the second derivative will be less than 0, right. You can simply think of a bowl and then look at the minima point, go in both the directions, you will understand. Clear? So this is your formulation for getting your regression. So this will be straightforward, okay. So you just need to do the what I call loss function or cost function, you can differentiate this function, you get 2 equations, 2 unknowns, right. This is the same thing I have written. So, this is 2 equations and 2 unknowns, you should be able to solve it. Clear? So, this is called normal equations, this is called least squares, because we are minimizing the squared error. So, we call it as least squares, and these are the normal equations after differentiating, partial differentiation. So, we call it as least squares, normal equations. When you solve these 2 equations, you get the beta naught and beta 1. Okay. By now you should have guessed it, if beta 1 should be a function of covariance or correlation, because beta 1 is the relation between y and x. So, linear relation between y and x, and we know linear regression between y and x 2 variables is given by correlation or covariance, normalized covariance which is correlation. So, beta 1 hat is actually a function of correlation. Okay. When you solve this, this is the equation you get. This is what you do in ANOVA also. Instead of I just gave you the formula, but the ideal way is to minimize the squared error. So, this is what happens, okay, beta 1 hat, and your beta naught is what? Whatever not explained by beta 1, whatever left behind, that is what? Y bar minus the average value, the average which is not explained by the x, the difference between the average and what is not explained by x is what your beta naught. So, that is where beta naught is y bar minus beta 1 x. Look at this, what is beta naught? Beta naught is y bar, beta naught hat is y bar minus beta 1 hat x. So, whatever is left behind that cannot be explained with regard to the mean, that is what beta naught is. That is why you call it as a intercept, the shift from the mean or the shift from 0, which is what you usually have at a center. The shift you can see, it is the difference between the mean and the whatever is explained by x. So, that is the shift to accommodate for the common mean part, that is what. So, what does intercept do? Intercept just shifts the mean value, that is why it is a function. You can see from the derivation, that is what it is doing, y bar minus beta naught x, beta 1 x, and beta 1 is a function of correlation. Clear? So, this is what the 2 parameters are. So, now we have done the linear regression part.